Well, good morning, good afternoon, everybody. Welcome to the day 3 of the training on weather and climate services for energy sector in Central Asia. We're almost halfway already with the course, and we hope that you're still having energy and motivation for today. There are quite a few interesting activities planned. And we hope that the past couple of days have been really great learning experience for you all. So today we are having 3 very experienced speakers that are not only doing high quality research, but also have they have been directly contributing to important projects which form the basis for weather and climate services for energy. We also today, as Alberto nicely presented on Wednesday, we will have an interactive activity in smaller groups where we will start our first, we will develop our own projects. And in those small groups, we encourage you really to actively engage and seek opportunity on receiving the feedback from mentors and group peers, group members, and collaborate to develop your first own project. So something interactive and different and refreshing for today. But first, I would like to introduce Claire Goddess, who will be giving us a short lecture on collaborative approaches to weather and climate services. Claire is a senior research fellow from Climatic Research Unit at the School of Environmental Science at the University of East Anglia. She's a key member of the international renowned Climatic Research Unit at the University of East Anglia, and her current research interests focuses on the development and use of regional climate information, particularly with respect to climate projections and forecasts, extreme events, and the representation of uncertainty. Claire works with the interface between climate modelers and users of climate information, where really communication, particularly with decision and policy makers, as well as researchers modeling the impact of climate change. She is really increasingly important. Her particular interest is in the energy and health sectors and in the co-design of climate information and services for these sectors. So impressive background and research that you have been covering. So we're very curious to hear from you. We tested presentations. So Claire, without any further ado, over to you. I just want to mention to everybody, we again have, of course, interpretation to Russian language, so you can use it below and select your language channel. Claire, please, over to you.
Okay, thank you for that very nice introduction. Good morning, good afternoon, everybody. And it's a great pleasure to have been invited to kick off the final day this week of your course, and I hear that it's been a great success so far, so I hope today will be as successful. So I was invited to talk about collaborative approaches to weather and climate services. Next slide, please. So let's start just by looking quickly at the learning objectives around that. So the term that I tend to use rather than collaboration, a sort of all-encompassing term, is co-production. So what we're going to do is look a bit at the principles behind co-production, what we mean by co-production, and then hopefully to learn from examples of co-production in practice that I've been involved with, and begin to appreciate some of the benefits and the challenges of co-production. So maybe you'll recognize the diagram on the right hand side of user interactions, showing the sort of different stages of developing, implementing a climate service. And so we'll touch about how co-production can impact and be used in those various different stages, but always with user interactions at the heart. The next slide, please. Okay, so let's sort of take a step back and think a bit about what climate services is trying to do. And essentially, climate services is trying to get us from, I guess, the world, the community that I originally came from, the climate science, the climate modeling community, which is a community in a world of a lot of data that's represented on this figure. You don't need to see the detail, but this is the sort of perspective from the international climate modeling community, the Cmip community that produces the climate projections, the simulations that underlie the climate projections that are used by the IPCC and I would say kind of universally. So you can see this is a very technical world of data exchanges, of terabytes of data formats, melding, observed data, climate projections. And on the other side of the diagram is the world of the decision makers, the user of climate information. The world of decision makers, policy makers, who, yes, they're interested in having and using climate information, but that's not the only information they're using to sort of make their decisions. So it's a much wider world where wide, broader social, environmental, political, financial issues become important. So the question is, how do we sort of bridge this gap, what's sometimes referred to in the literature as the usability gap? How do we bridge these two different communities? So next slide, please. Okay, so this is where climate service. If you can go back one, please. I think you've gone forward. If you could go back to the, yeah, back one more. Yep, stop there. Yep, perfect. Thank you. Okay, so what we want to do is we want to get to from this world of terabytes of climate model data, of hundreds, if not thousands, of technical and scientific papers, to information that's useful and usable. So essentially, the world of climate services. Now, if you read the climate services literature, and particularly papers published over the last 5 years or so, you'll come across terms like credible, salient, and legitimate. And this is what is really desired from climate services. So saliency really relates to this idea of having useful and usable information, not just data. And then there are also issues around the trust in the providers, the quality of the information. So the information also needs to be credible and legitimate. And I think you'll see, if you read the literature, and talk to those involved in the climate services community, there's been an increasing recognition that climate services are more likely to be credible, salient, and legitimate if they're co-produced. But you'll also see terms like co-designed, co-developed, and co-evaluated. So next slide, please. So what do we mean by co-production? You'll hear people talk about co-production much more broadly in the scientific research community, but here we're interested in what we mean by co-production for climate services. And so here is a definition that I put together with colleagues based on previous papers. So it's a relatively short definition, but I would say that each word we chose very carefully, and each word is there for a reason. And each word, as we'll see, to put into practice requires quite a lot of thought and effort. So co-production is a sustained and collaborative process between scientists and decision makers, so between the providers and the users, if you like. it is collaborative, but it's also sustained. So it's not something that just happens, you know, kind of once off. It's a sort of long-term commitment for the production of useful, actionable, and socially robust knowledge. So unpicking each of those words, we'll do a little bit of that. I won't be able to kind of cover everything, but actually requires quite a lot of thought. The second quote is one of the quotes that we kind of use to arrive at this definition, but you see the same sort of words appearing. Now, I'll probably use different terms, and as I said, you'll hear people using different terms like co-production, co-design, co-development. So maybe as I talk, you can think about, are these the same things, or are they essentially the same things but happening at different kind of points in the production cycle? So next slide, please. So having talked a little bit about the sort of theory and the principles, what I want to focus on now is two practical examples of kind of trying to implement co-production in the real world. And I'm going to draw on two projects that I was involved with. One is the Esem project that was Copernicus Climate Change Services project, and the other is the European Horizon 2020 Seclifern project. And as I talk and tell you a little bit about these projects, maybe you can think about, for you, do you think that they're good examples of co-production? If so, why do you think they were good examples? If not, why not? What could we have done better in the project? And the other thing to sort of think about is the level of engagement that you think we were able to achieve within the project. So here is this diagram here on the left hand side shows three broad categories of engagement between users and providers of climate services, from a paper by Chris Hewitt and colleagues. And so it starts here with information provision, which, if you like, is quite a kind of top-down thing. So it might be a climate service provider developing a web portal with perhaps a fairly minimal amount of engagement with users, maybe having some workshops asking users what they want. But essentially it's about information provision, and it's perhaps more of a kind of one-way process. But what we have in the middle of this orange box is more a dialogue-based process. So much more of a two-way process of engagement with users. And you'll see here that it actually kind of refers to co-production as happening in this box here. And then at this top level, the blue level, you have this area of active engagement with very focused relationships, sort of perhaps more one-to-one relationships with a user and a provider, could be involving sort of facilitators or boundary organizations, but very, very highly focused perhaps on a specific sort of user problem. I mean, in reality, there's probably much more of a kind of a sort of more blurred transition between these sort of different areas of engagement. As I say, as I tell you a little bit about Esem and Seclifern, think about where you think these projects kind of fell within this within these categories. Okay, next slide, please. So the first project I want to tell you a little bit about is European Climatic Energy Mixes, Esem, which was funded by Copernicus Climate Change Services. It was actually led by Alberto Chocli, was the leader of the project. And this project had the aim of producing a pre-operational proof of concept climate service for the European energy sector. Now, we weren't trying to provide everything for everybody within the energy sector, but we started off with a kind of general idea the type of service that we would be providing. So a service focused on electricity demand and renewable energy generation. So allowing users to look at large-scale patterns of the demand-supply balance across Europe and the sensitivity to climate drivers, both historically, both in terms on seasonal forecasting timescales and in terms of longest timescale climate change projections. And so based on this and the general concept for the service, we as everybody should do when you're thinking about developing a climate service, we thought about the target audience for this climate service. So yeah, so the most obvious groups, transmission, distribution systems operators, energy companies. I would say that one group that turned out to be more important than we originally thought of were commercial climate and service providers for the energy sector, so consultants. And there were a number of others, but I would say these are the kind of main ones. So what we were endeavouring to provide for our users were three things. One was a demonstrator, so a sort of user interface, a visual portal referred to as a demonstrator. And here is a page here showing you the sort of map of Europe and some data. So yeah, embedded. So this visual portal is how we provided the energy and the climate data, but also embedded within the portal was guidance and know-how. So next slide, please. Okay, so the schematic diagram sort of summarizes the process of stakeholder engagement that we used throughout the project, the timeline from the start of the project in November 2015 through to the end in March 2018. And it was very much an interactive and an iterative process of engagement between the sort of technical team and potential users. So we started with a fairly broad first vision of how the demonstrator, the sorts of things that it might be able to do. As I say, we knew that we were thinking about a fairly large scale information, so sort of typically country averages or sub-country averages, rather than going down to individual sites. We had some idea of the sorts of climate and energy variables that would be relevant for users. So obvious things like temperature, rainfall, but also sunshine, river flow, and in terms of energy, clearly demand, hydro, wind, solar production. But we didn't want to kind of constrain things too much at the beginning. So in our first interactions with users in workshops, we presented a fairly broad and general vision. And after listening to users in the first workshop, we then began to sort of build what we call the logic requirements, but beginning to sort of build a picture of how the landing page for the portal might look, the sorts of display functionality, menu choices, and so on. Then built a first version with sample data to show the sort of look and the feel of the demonstrator. And then again, shared that with potential users at a second workshop in London, got some more feedback, then developed what we call the wireframe, which was essentially the first version with working links, which began then to allow users to do some hands-on evaluation and testing to feed back to us. We had another big workshop with another project that was developing a sort of parallel demonstrator system. So this was in Barcelona, February 2017, again updated. Another workshop in Italy, and then in October 2017 the final version was ready for a pre-operational phase. And we were able to do some more evaluation. Users were able to provide feedback. And so eventually a proof of concept was launched by the end of the project, was launched at a workshop. And again, after more evaluation and refinement. So I say the main method of engagement with our users was during these workshops, these series of workshops and symposium, 5 that happened throughout the course of the project. During these workshops, we used things like participatory exercises, but very much focused on the users and their decisions. At later stages, we ran hands-on sessions during the workshops. But as well as those, we also, there were feedback forms available. So from the demonstrator, the early versions of the demonstrator that users could fill in. We also ran surveys and polls. We also had feedback from a very active advisory board. We also ran a number of webinars that also gave us feedback. So next slide, please. And this infographic tries to summarize the, if you like, the Esem journey. So actually at the end of the project, we kind of reflected back on what we'd done, what we'd achieved, and that's written up in a journal paper in Climate Services. So the Esem project was very much built on partnerships between the project team, external stakeholders, and at the beginning of these projects, these were very much potential users. And this is summarizing what we felt that we achieved during the project. And clearly there were technical things in terms of learning about the data and so on, but I won't dwell on those so much. But focus more on things like, I think we achieved an enhanced collaboration engagement. We were beginning to see some new users and champions, by which we mean potential users who are happy to kind of go out and talk to others in their community, either in their own company or more widely at meetings. And I think we were kind of beginning to see the emergence of a community of practice. And that has further developed beyond the end of Esem. So the proof of concept Esem demonstrator provided the basis for the development of C3S energy, and operational climate services that is very much linked to the Copernicus climate data store. And now is run, as I say, as an operational service. So, and marking that step from pre-operational to operational, actually the project leadership changed from the University of East Anglia to WEMC, although Alberto was still the person in charge, but kind of reflecting the next stage in development. So I think now with at this stage very much a stronger community of users and target users. But actually, even beyond C3S energy, there is yet another stage of development, and that's the kind of development of commercial products and services by consultancies, by others, off the back of C3S energy, which then is beginning to sort of contribute to a much more well-developed market for energy climate services across Europe and beyond. Down the left-hand side of this figure, TRL stands for technology readiness levels, which I'm not going to talk about, but you can read about that in the climate services paper if you're interested. But you can see that I think we've actually through Esem and kind of beyond, we're really raising the TRL. Okay, so that was a quick run through Esem. So next slide, please. Okay, so I'll now talk about SECLIFERM, a Horizon 2020 funded project that was also led by Alberto. But here the approach was kind of somewhat different. And I would say we were in Esem, we were interested in more of perhaps a kind of generic service that would be useful for a wide range of users. In Seclifirm, we were much more focused on individual users and, very importantly, their decisions. And the other thing about Seclifirm is that we only focused on seasonal forecasting and decision making on seasonal forecasting timescales, so see up to sort of a season or so ahead, rather than the longer timescale climate projections. But because of this focus on decision making and sort of individual users, we took a case study approach. So we at the proposal stage, we'd identified 9 case studies, mainly focused on the energy sector, also one more focused on water. And this is the diagram that you'll recognize, but actually if you look closely, this is the diagram reinterpreted, the WMO diagram reinterpreted from the Seclifirm perspective, with climate services co-production at the heart. And again, the kind of different stages through framing, identifying user needs. Something I'll talk about that was, I think, very particular to Seclifirm and very useful was the development of what we call decision trees. The tailoring of seasonal forecasts, the more technical part of the work. And then another key aim of Seclifirm was to assess the value add to the users of having the seasonal forecasts. I won't say so much about that, but I'll touch about it a little. And then we also developed trial climate services for each of the case studies, and I'll say very little a bit about that, but also I'll also talk about co-evaluation as well. Okay, next slide, please. Okay, so so this shows the Seclifirm case studies, and here we refer to them as co-designed, and using the phrase co-designed here because they were actually identified at the proposal stage. So for the proposal, the research team came together with industrial partners. So a number of the industrial partners, well, some of them were actually formerly team members, but they were all involved in the proposal and gave their endorsement to the proposal. So each of the case studies was built on these partnerships between industrial and research partners, which is shown kind of graphically here with the logos, and also shown here. So say most of the case studies focused on the energy sector. So things to do with balance, in some cases balancing demand and supply, for example, for some of the NL, the Italian company case studies. To mention case studies 6 and 7 involved offshore production. So they were interested in offshore maintenance, for example, so interested in offshore wind and wave conditions. One case study 9 with the UK Met Office and Thames Water focused more on water. So they were all had a geographical focus, and a lot of them were focused on particular types of extreme events that had been identified at the proposal stage of having had an impact and perhaps caused problems for the company in terms of finances or operations. So for example, an Italian heat wave, some sort of wind events, and so on. So I'd say what was at the heart of the project were these partnerships between the industrial and the research partners. And so most of that interaction happened, well, kind of one-to-one or in small groups. So in regular meetings between each of the industrial and the research partners. So for example, the UK Met Office had regular meetings with Thames Water for case study 9, with National Grid for case study 8, with Shell for the case study 7, the offshore one. So these were kind of very, very much close relationships that sort of developed. And so yeah, it would be the Met Office managing the, when the meetings were going to happen with their industrial partners. Similarly for KNMI, the Dutch Met Service with TenneT, and another energy company based in the Netherlands. But next slide. So although most of the interaction happened, I would say, in sort of small groups within each of the case studies, we did also come together as a project for interaction. And I want to give the example of co-development of decision trees. Now, this is something that actually started, well, we tried doing it. We thought it would be a good idea to try and do it at one of our workshops in Milan. And this was very much as the participatory activity. So kind of what happened, the two people standing here are from people from Shell and from TenneT, so from the industrial partners, so people whose day job is to sort of manage offshore maintenance of getting ships out to offshore structures, to manage the maintenance. And so they're interested in the probability of particular thresholds, of dangerous thresholds of wave height or wind speed being exceeded, which means that they then can't go ahead with their operations. And their interest is in these vessels that for offshore maintenance are very expensive, so they really need to know when to kind of go ahead. Ideally, they want to book the vessels kind of ahead of time because then it's cheaper. And they're also interested in, is it possible to extend maintenance into the so-called shoulder seasons outside of summer, when the vessel should be cheaper to hire. So what happened in this workshop is we kind of interrogated them. We asked them about their decision-making process. And this is Laurent Debout, who I think is involved in this course. So as the people gave us the industrial partners kind of explained their decision-making process, he interpreted it for us in real time in this kind of flow diagram. And this is the decision tree that came out of the workshop. After the workshop, it was tidied up and was actually used in these two case studies. So next slide, please. Okay, and from that experience in the Milan workshop, and the experience working with Shell and TenneT, actually the other case studies decided that this was a really useful, that these decision trees were a really useful tool. So eventually all of the case studies developed their own decision trees, which took quite a bit of time in some cases, because the companies hadn't put their decision-making process kind of down on paper. But we found them, I think everybody found them to be a really useful tool. So to provide a systematic and a consistent visualization of the key decisions, especially the climate-driven ones. Okay, this is an example actually of a simplified decision tree used by Enel, the Italian energy company, in their case studies. Actually, they had a very much more complex decision tree which was used internally, but because that included confidential information about their decision-making process, which is just shown in this one box here. This is a sort of public version of the case study of the decision tree. But what the decision trees also allowed us to do was to identify the points of the nodes in the decision trees where improved climate information and forecast could be input. So in this case, it's the top row, but in the one we were looking at on the previous page, it comes right in the sort of middle of the decision tree. And then also allows you to see the point at the end where the value of adopting the information can be assessed. So in this case, for Enel, we use some quantitative performance indicators after econometric modeling. And also allowed, I think, the partners, the industrial partners, to think about how to embed probabilistic information within their current decision-making processes. So I would say at the start of the Secley firm, most of the partners weren't using any kind of seasonal forecasting information, but were using what we call climatology, so sort of typically 30-year averages or some sort of average climate information, and making their decisions on the basis of that. So in the Enel case studies, for example, they were able to evaluate the sort of difference in terms of the outcome of the decision, in terms of using climatology or using the tailored seasonal forecast developed by Secley firm, or actually by using the kind of real-time data. So next slide, please. Okay, so just another word about the utility of decision trees. That yes, we use them in quite a formal way, as we saw on that kind of previous example, but I think one of their greatest utilities was actually in the process of co-developing them, that they really provoke useful conversations and sharing of critical information. And that was certainly the case when thinking about user needs and decision making. And I think the experience of the lessons learned from Secley firm were very much that you can't separate the needs and the decisions. That also needs evolve and develop over time. So right at the beginning of Secley firm, we did sort of ask our users, okay, what do you want from us? And they told us what variables they thought they wanted, what time and spatial scales they wanted. But actually what we ended up providing at the end of the project and was most useful to them look somewhat different to that kind of those initial needs that have been developed. So I think the message is that identifying needs it's not a one-way process, it's not a linear process, and it's not a quick process. So you need to kind of go back. So it's very much iterative. Okay, next slide, please. Okay, so thinking a little bit more about co-design, this time of the trial climate services. As I said, we developed a trial climate service for each of the case studies, so typically some sort of visual tool. And this example comes from the case study between the Met Office and the Thames Water, which focused on maintenance in the water sector. And this again is another sort of timeline. So in some ways similar to the timeline I showed for Esem, but here actually just for an 18-month period in the final stages of developing co-designing, co-developing the trial climate service for Thames Water. And I think the point I want to make is that actually this interaction became really kind of very, very intense and very frequent at the most critical points of co-development. and co-design. And that the industrial partners, the users, were kind of critically involved in workshops, for example, agreeing the initial format of the trial forecast climate service. And so from November 2020 onwards, the trial forecast was disseminated to Thames Water twice a week. So this included some shorter timescale information as well as the seasonal forecast, but really very regular meetings to review the service, to discuss the visualization tool. And I think the visualization was modified. Also, the guidance provided with the tool was modified. And again, there was time for, it was also shared in between different case studies, so some cross-sectoral, some cross case study learning. And then there was also a real-time case study evaluation though around a particular event in January, February 2021. So then that brings us on to thinking about evaluation, co-evaluation. Next slide, please. Okay, so when we think of co-evaluation in the context of co-producing climate services, there are a number of different things that we can can be evaluated. So it could be the actual process of co-production, the quality, the effectiveness of stakeholder engagement, exploring the extent to which communities of practice have been developed and can be sustained. And I'll say these are areas of co-evaluation where it's particularly critical to bring in social science expertise. And these are important areas, but actually what we focused on in SecLiFirm is evaluating the outputs and the outcomes. So thinking about what it was that we'd actually produced and developed in terms of the kind of data sets and the trial climate services, but also the outcomes in terms of the decision making for the industrial partners. So thinking about the outputs and outcomes in terms of quality and economic and practical value. So this schematic shows the overall approach to assessing the value add to the users in SecLiFirm, which I sort of already touched on, that essentially we were comparing this control case, so the position at the start of the project with users only using climatology, for example, calculated from Reanalysis data, compared with using the tailored seasonal forecast. Next slide, please. Okay. And kind of one message, I think the only message I want to kind of say now about our assessment of value add, remembering that here we're talking about seasonal forecasts, and so we're working on verifiable timescales, is that the forecast skill and value are not the same, thing. So this diagram actually comes from one of our offshore case studies, so looking at the probability of exceeding thresholds of significant wave height. And this actually shows the Brier skill score, which is a metric that the seasonal forecasting community tend to use to evaluate their skill. So here looking at skill out to 30 days ahead. So 1 is good, 0 shows where the forecast is performing no better than climatology. And here we show the results for the different seasons. This is a location in the North Sea. Essentially here you can see that the skill falls off very, very, very rapidly, and by about 10 days there's really no skill, very little skill compared with climatology. But when you look at this metric of relative economic value to the user, and particularly for the highest wave thresholds of greater than 3.5 meters in red, yes, the value does kind of fall off about 10 days, but actually here the value is maintained out to 30 days ahead. So here it shows that there's greater value to the user in terms of having and using the forecast than you might think if you only looked at the forecast skill alone. Next slide, please. Okay, I think I'll skip over that one for time. So next slide. Okay, so this is my summary of the benefits and the barriers and challenges of co-producing climate services. And hopefully you can maybe add some more of your own. So the benefits, I would say, in better outputs and outcomes, in terms of more credible, legitimate, salient services. So I think greater trust in the providers of the services, a better understanding of users' requirements, and particularly in terms of the role of climate information in the user's decision making. And I would say on both sides, both the providers and the users, much greater sense of ownership in the final product. So really helping to build capacity of both the providers and the users. The barriers and challenges, I think the scale of the time commitment, language differences, by which I mean kind of technical language. The word scenario, uncertainty, forecast skill means different things for different people. Different communities tend to use jargon. There were also some issues of confidentiality and commercial sensitivity, working with some of our companies, but I think we managed to get around those. And here I would say the trust really helps. In Seckley Firm, we certainly had economic experts on board, but I think the scope to co-opt and bring into the process perhaps a wider group of social scientist experts, for example. Okay, next slide. Okay, there's some reading for you. This is the Esem Climate Services paper. You can find out more about the Seckley Firm case studies from the website, but also we're currently working on a number of papers that will appear in this special issue of the journal Climate, so go and keep an eye on that. And here are some other reports on co-production of climate services that might be interesting for you, including this very recent one from the ERA4CS consortium. Next slide, please. Okay, what we learned, well, hopefully now you can, in a better place to answer these questions. What is co-production? Why is it worthwhile? How can we implement it in practice? And maybe also you can kind of answer these questions that I posed to you. Are Esem and Seckley Firm good examples of co-production? If so, why? If not, why not? And what level of engagement from passive to active do you think they attained? Okay, that's my final slide. So I'll stop there, but maybe if you want to leave this slide up during the okay, yeah. I don't know if we want to leave one. I don't know if you want to leave up the one before for the questions.
Thank you so much, Claire, for this impressive lecture. Really impressive work, and for me it was really interesting to hear the different approaches you took for Esem project and the Seckley Firm. I encourage participants to send quick questions in the chat to Claire. We still have a couple of more minutes before going to our group work. But maybe while our participants are thinking and typing, I would have one question in particular to your work on Esem. Really, it was a huge project with many stakeholders. And you already highlighted in your presentation how important it was really to bring everybody on board. And I think you took in the process quite strategic approach by bringing different stakeholders in stages. Maybe if you could share a little bit more about what are challenges that you were facing? I think it would be interesting for participants to hear what was the process like, how you managed to really like convince to bring those stakeholders on board to really create like a more robust model together and finally service for a wider use. If you could maybe shed some more light on that, I think it would be really appreciated and interesting for the participants.
Okay, I mean, I think the critical thing is to kind of get the right people in the room. So as I say, you can sort of think we had some rough idea of the different types of organizations that might be interested. And I would say that networks, also existing networks, were kind of really important. But I mean, I would say also it's important not just, for example, to identify, you know, the particular company that you think might be interested, but to try and identify the right individual within that company or individuals. I think that's kind of really critical, and it needs to be somebody with some commitment, with the and with time. But it's maybe what we call like a kind of snowballing kind of effect. So yeah, what more can I say? Well, I would say that, yeah, these, what we call these kind of champions, are kind of really important. Things we did were in terms of sort of was going out to sort of talk to potential users, as well as organising our own events. So team members would go to sort of sectoral meetings. So if there was a particular energy type meeting, I mean, I think Alberto would actually be better placed than me to kind of talk to you a little bit more about this. But so actually going out, maybe having a short presentation or a poster in a kind of sectoral event, so you're not expecting somebody to travel to something that's only on climate services or only on Esem, but, you know, is kind of part of an existing event. I think there were also sort of phone calls and things, so kind of identifying particular individuals, some one-to-one phone calls. I think the webinars were also very useful. And I think as you kind of begin to sort of demonstrate the value, you know, yeah, things kind of do snowball.
Yes. Interesting. Thank you so much. The start is tough, and to really get the right, as you highlighted, champions, to really develop ownership in the experts that you targeted as your value add experts or champions. I think it is tricky, but in your experiences here and examples, it really paid off. And thank you for taking time and sharing this impressive work with us. I see that there are no additional questions in the chat, but there is quite a bit of interesting literature for everybody. So I encourage everybody to peek in, to look and have some additional reading. Now, without any further ado, I would like to hand it over to Alberto, who will introduce our next workgroup session. And Claire, thank you again for a fantastic lecture.
Thank you very much, and I wish you success for the rest of the course.
Thank you. Thank you so much. Alberto, over to you.
Yeah, thank you. Thank you very much, Eva, for handing the session here, the first part, very well, and of course Claire for the great lecture as usual. And we're now moving to the session on the working groups. So on Wednesday, on session 2, we went through some of the instructions that may help during the working groups. And now today, and then Monday and Wednesday again, we will have 3 hours of working groups. And like I said, on Wednesday, there is a possibility, if you wish to extend it somehow, by arranging between yourselves to meet outside of this hours. But let's get into that. The first task here now, having given all the instructions last time, we only need to now put people into groups. And we've done that work based on the suggestions you sent also to Dinara. So thank you for sending the suggestions, and thank you, Dinara, and the rest of the team with Beatrice to sort out all this, the groups and forming the what we have now, it's 5 groups. 5 groups of 10, 11 people each, which was the target, so that's great. Each group also has a mentor, and so what we're going to do now, I think it's all set. If Dinara gives me the green lights, you can see your name here listed on these groups. Each group will be assigned to a breakout room. So if I understand correctly, everything is set and people will just need to join the group with their name. Is that correct, Dinara?
Thank you, Alberta. Let me explain in Russian to the participants how to proceed. Здравствуйте, участники. Как вы видите, ваши имена сейчас видны на экранах. Пожалуйста, внимательно посмотрите, в каких группах вы находитесь, и вы можете сами выбрать тот зал, в котором ваше имя находится. Если вашего имени нету в списках, я вижу сегодня новые имена, то вы можете в чате написать, мы вас перенаправим в соответствующую группу. Если есть вопросы, пишите в чате, мы вам ответим. Спасибо. So, Alberta, I just explained how to proceed for the participants. They can go, they can assign themselves according to the list, or in case they have confusion, we will assign them on our end.
Okay, excellent. Thank you very much, Dinara. Just one thing I want to add is that, as you can see from the slide, we have 4 groups who are going to be with the Russian-speaking. Well, I think it's all Russian-speaking. So if you don't speak Russian, probably you don't want to be there. And instead you go to group 1. So you see group 1 is English speaking. So the moderation, the people mentoring there will speak Russian in the 4 groups and English in the first one. So there's no, I understand there is no interpretation, I'm afraid, in the working groups. So you have to rely on the mentor to get some knowledge. And if you're in trouble, I will be outside here in the hall, in the main room, and maybe the mentor can come out and ask me, or ask me to come into the group, and I will come, or someone else will. So I guess we can start. Just remember, we are coming back. Let's finish this. You can take a bit of time also over the break. The next lecture is going to be at 11:30 UTC, so in an hour and a half. So you can take an hour and 15 minutes even if you want, and then you take a 10-15 minute break before the next lecture. So let's go into working groups and have fun and work hard also towards the Obini proposal. Thank you. Hello, everybody. We're back from the break.
Yeah.
Yes. Are we ready to go? We have still some people probably have left the meeting. Coming back. Okay, so I hope you had a fruitful discussion during the breakout groups. I've attended a couple, one of which I couldn't follow very much due to the language, but there seemed to be a good discussion. So let's hope we get some good projects, and maybe they will get funded eventually. So we'll now start the third part of this session with 2 great speakers. And we're going to hear about the weather and climate forecasting for energy. So this is the next step in our training. We learned about the services, we learned about the situation for energy in the region, we learned about co-development, co-production approaches, a lot of very useful background information. And now a little bit more on the technical side, and so we can see how we can produce useful forecasts. And to start with, we have Dr. Sue Holt from NCAR, the National Center for Atmospheric Research in the US. And she's a senior scientist and deputy director for research applications, and also a contributing director of the World Energy and Meteorology Council. So a very close colleague and collaborator of mine, which is a great pleasure to be. And she leads projects in renewable energy prediction, coupling mesoscale models to microscale models and in applying artificial intelligence. Sue is an expert in applications for artificial intelligence in environmental sciences, boundary layer meteorology, large-scale atmospheric dynamics, renewable energy, dynamical systems, and plus a very long list that follows, and including a lot of publications, books, and so it's a super pleasure to have Sue here, particularly because Sue was keen to be here with us. And being based in Boulder, near Denver in Colorado, you can work out the time there, which is 4:30 in the morning. So we're very grateful for having Sue here. Over to you, Sue. So you have, you know, how you then have about 25 minutes, and then I'll introduce David when you finished. Over to you. Thank you very much, Sue, for being with us.
Thank you, Alberto. It really is a pleasure to be here this morning. And I'll be, as you know, today we're doing a session on weather and climate services. I'll be talking more about the shorter range scales, and David will cover some of the climate scales. So some of the things that I want to point out today is, first of all, the atmosphere varies on a variety of scales in both space and time. But we can develop methods to make predictions of the atmospheric variability. We'll be talking about using dynamics and physics, as well as applying machine learning and artificial intelligence as part of these prediction methods. And as we do that prediction, it can help us manage our energy systems more effectively, efficiently, and economically. So first, to the variability. This first movie that I'm showing is the variability of the atmosphere from a model, a climate model, over the period of months. And you can see in this image how there's a constant varying in the cloud cover, as well as in atmospheric moisture, all the variables that we care about that impact us and that impact our energy system certainly do vary on these longer, larger global timescales. But they also vary on continental scales, where here you can see a weather system, a cold front, warm front moving across the United States as it forms and progresses across the country, certainly makes a difference to the people who are living there. As for the impact on energy, you can see that when we get to wind plant scale, there's turbulence that impacts the wind plant. And more than just turbulence, large changes, such as when a weather front comes through a wind plant, changes the wind direction and speed. In that case, of course, we're going to have to operate the plant a little bit differently. And then this turbulence, this variability does impact on the turbine scale, making a difference in how the turbine operates, how long it lives, how it's able to operate because of this turbulence, and how much energy is produced. So we generally have a flow from larger to finer scales, but there's additionally a flow back of this energy. So to harvest this energy, we need to understand its variability. I'll be talking a lot about renewable energy here, but let's start thinking about the impacts of changes in weather and climate on the energy system. I suspect Alberto talked about something similar in his introductory lecture. We're on very short scales. We have things like lightning that can cause flickering in systems. Passing clouds on the order of minutes can decrease solar power. Passing thunderstorms disrupt energy transmission and distribution. Tropical cyclones have a big impact. When we have drought on scales of months to seasons, it reduces the hydropower. When we have cold and heat waves, it changes our demand picture. And then the longer scale interannual variability can make an impact on how we plan for maintenance, et cetera. And of course, on the longer scales, we end up with a changing climate that can impact the energy system in lots of ways, such as changes in the renewable resources. Now, today I'm going to focus on weather to seasonal timescales and talk about the planning needs to run renewable plants, where we want to be able to predict the hub height wind speed of turbines, the solar irradiance that is important to optimally running grids that have a lot of solar power, and then of course stream flow for areas with hydro resources. So the idea here is that we want to forecast the variability and make it easier to integrate these renewables into the grid. So on the very short time scales for the renewable plants, we need to be able to integrate in the grid. Here we're talking on the order of minutes to hours. At medium range, we need to be able to plan ahead for day ahead operation and which resources are going to be running at which times. Longer ranges, weeks to seasons, what we often call subseasonal to seasonal, or S to S, we can plan for maintenance, distribution, et cetera, and then very long ranges, resource allocation planning. Now, each of these scales, we can bring different technologies to play. For instance, on the very short time scales, we may have sensors right in the wind, solar plants, measuring stream flow, et cetera. But then we also have satellite, the remote sensing from space type measurements that help us forecast on the order of hours. And then there's this whole range of numerical weather prediction, from very specialized forecasts that can be run hourly to our global models, such as come out of the national centers. And then, of course, seasonal modeling. The national centers run ensembles of these numerical weather prediction and climate models. But we often use machine learning methods across all of these scales to blend the information, to optimize the information for our specific needs. And then in the end, we're going to blend all the information from all the models into a seamless prediction, convert it to power so the energy operators can use that. And in addition, it's useful to quantify the uncertainty in the prediction so they know what the predictability is at that particular time and end up with a probabilistic power prediction. So how do we do this type of Earth system prediction? Well, we know something about the physics of the system, of course. We understand water cycles. We understand how radiation warms the Earth, how it causes upward motion, which then can cause water vapor to condense into clouds, precipitate out. causing clouds that impact also the evaporation over the oceans and streams. So this hydrological predictability, we're able to estimate water stored in the snow as well as in the soil. And the meteorological predictability, we can forecast weather based on the differences in the temperature that causes wind, clouds, precipitation, etc. So, as I mentioned, there are numerical weather prediction models that are based on the physics and the dynamics of the system. The dynamics are basically a series of partial differential equations. We won't get into those details today, and I'm sure you'll thank me for that, where we integrate the equations of motion forward in time. But to get all those processes like radiation transfer, cloud formation, boundary layer processes that make the weather, we have to parameterize physics that occur inside that we're not able to model directly. And of course, we need to have correct initial conditions based on observations. We pre-process data that has been taken across the globe and assimilate that into the models. We run these models, post-process them by blending information. And of course, there always have to be steps like validation, assure the quality of them, etc. Now, it's very important to consider the difference between what we can do on global scales, for these long-range predictions versus what we do for weather. And a lot of the difference that it makes is the resolution that we can run the models at. As you can see here, if we're trying to resolve terrain, the climate models that run at about 100 kilometers resolutions are not able to capture the complex terrain that includes the mountains that we can get at the 2.4 kilometer resolution. Well, what difference does that make if we don't resolve the terrain? It can make a huge difference. Here we're showing plots of snowpack in the Rocky Mountains, the Central Rockies, here where I live in Colorado, as modeled at 36 kilometers on the left. Here, this is a particular April 15th, where you can see that it's very spotty what we're able to capture, and we aren't able to get what happens in the valleys and the detail that we can get when the same thing is modeled at 2 kilometers. And when we compare to measurements from the SNOTEL network here in Colorado, we see that we need this high resolution to be able to get that fine detail of the snowpack that's going to make a big difference to the stream flow throughout the rest of the year and make a big difference for hydrological planning. So being able to do these fine resolution models does make a big difference. Okay, so I did mention that we assimilate real data into these models. And it's the observations that are taken. Some of those are surface observations. We may have sensors directly in the wind plants, the solar arrays, stream flow measurements. Those really help get the model, start the models out accurately so that we can make a big difference. In addition, remote sensing, such as from satellites or from radar that are in the region, can really help get the models correct. Atmospheric profiles, we launch weather balloons throughout the world at least twice a day. That gives us a lot of information about the structure of the atmosphere on a vertical basis. as well as very specialized data. And here I've shown the picture of a wind cube LiDAR that's sometimes used near wind plants to be able to measure the wind in that region very specifically. And if you're running local numerical weather prediction, those data can be very helpful as well. Now, I like to think about forecasting for renewables in terms of a value chain, where here on the left, and this is one that is specific to solar power forecasting, we had a rather large project funded by the US Department of Energy, and we worked with the stakeholders to think through how to go from weather that happens, and for solar forecasting, it's primarily clouds and aerosols, to providing economic value. So basically improvements in how the production is done, how the utilities are able to use their reserve, and that has direct economic benefit to the stakeholders. And to get from the weather to this economic value, we include monitoring. Some of that are the ground-based, some of them are remote, such as the satellite data. Various types of models, some of which are numerical weather predictions, some of them are machine learning, bringing all of this together into day-ahead and very short-range forecasts, and communicating it to the user, the decision maker, via point forecasts or area forecasts, depending on what they need to see for their use. Converting to power, the variable they really care about, quantifying the uncertainty so that they can project the power production, compare it to actual, use that information to balance the loads for day-ahead planning and real-time operation so that the unit allocations are more efficient to make this positive change in production costs as well as reserve usage. So when we built that solar power forecast system, and this was the gold-plated system because it was on research dollars rather than what was actually employed, we had lots of different types of models. Here on the top for day ahead, we're using various both customized numerical weather prediction as well as global models, local observations for the nowcast system, bringing in satellite data, total sky imager data, local observations, satellite data, etc., blending them all and having bringing together day ahead nowcast into a seamless forecast, converting to power, providing a probabilistic information. And here, all the segments of this that are an artificial intelligence-based method are outlined in red. So you can see that we bring that in as part of the blending and as some of the short-range prediction methods themselves. We've done this with both wind and solar for Kuwait recently, in which case, again, outlined in blue, we have the numerical weather prediction models, and in red, the AI models. So I've talked about numerical weather prediction. What are these AI machine learning models like? Well, you'll notice on both of these at the center, we're using what NCAR calls a dynamic integrated forecast system, or DICAST. And its goal is to integrate the numerical weather prediction models to produce an improved forecast. So bringing in both specialized numerical weather prediction as well as global models, such as the US Global Forecast System, Canadian system, often include the European system, whatever is appropriate for the country. Integrating them after you do a correction, a bias correction of each, using the nacelle winds at a wind plant to as the truth that you're trying to correct to. Again, we're going to convert to power to provide a power forecast, but using the information that is most important to the plant, and in this case, the hub height anemometer right on top of the nacelle. And when we apply systems like this, we find that we typically get a 10 to 15% decrease in error over the best of the numerical weather prediction models. And that can make a big difference in efficient, effective operation of the wind plant. Okay, so when we have information in the plant, such as here in Kuwait, we have 3 weather stations, such as the one shown on the right, located directly in this plant. And we have observations of air temperature, panel temperature, wind speed and direction, relative humidity, etc. Can we use that information to build a machine learning model of that short range variability? And indeed we can. And in this case, we used what's known as a model regression tree, a particular system called Cubist. You can use lots of machine learning methods. Here on the left, we're comparing the Cubist result error in the purple curve on the bottom to here, the red curve is persistence. Now for solar, when we talk about persistence, it's a smart persistence where we allow the solar angle to change in time, but assume that the atmospheric conditions remain the same. And you see that the error is less for the Cubist system. Now in the blue curve, we want to see if we can beat the die-cast system as well that blends the numerical weather prediction model. And indeed we do. Die-cast beats the persistent model at about 45 minutes. And
во-первых, Химжанову давай не будем трогать, сейчас заведующая кафедры, такая вредная, с ней не будем, убирай. Потом ты говоришь слово дали этому Завгороднему.
And we see here on the right that when we're comparing to the already improved die-cast forecast, very short range prediction, it's 50% better. And then after a couple hours, it evens out to about 20% better. Of course, the operators don't want to see all the details of the models. They want to see the end forecast results. And that's what we provide them in this dashed green curve. But then they want to know what the uncertainty is. So we quantify the uncertainty. For this system, we use a process called an analog ensemble. I won't get into the details, but the darker shading around the prediction is the 25th to 75th percentile, and the lighter shading represents the 10 to 90 percentile. Now, when we do these forecasts, I did mention it does have a real cost saving. And in fact, when we worked with Xcel Energy in the United States, they looked at the improvement over time. When we started working with them in 2009, their typical forecast error was about 17%. By the time we delivered a system in 2014, it was down to about 10%. That's a 40% improvement, which they calculated over a period of 6 years, saved their ratepayers $60 million. Real cost savings by running the wind plants better, and this is for the day ahead timeframe in particular. Now, because that enabled them to run their wind more often, it also saved the world to over 260,000 metric tons of CO2. Big savings in terms of carbon in the atmosphere as well. Now, my colleague Jeff Lazo worked with Excel Energy on valuing the solar forecasting system and found that, by the time they had deployed more energy, it would typically save them about $820,000 per year. Now, he used that to estimate annual national savings for the reduction, the 50% reduction that we've found for them in solar prediction, and found that it would save on the order of 10 to 21 million per year across the United States. That would result in a 26-year savings of about $500 million. Very real cost savings. Now, David's going to talk about climate scales in a minute, but to bridge the gap between the weather scales that I've been talking about and the climate scales, I just want to talk about seasonal forecasting very briefly. You can do that in a very similar manner to these shorter time scales. And I want to talk about a paper that was co-written by one of my new postdocs, Will Chapman, at University of California, San Diego, where they began with data from NCAR's Community Earth System model, that is a 1-degree climate model. The large Ensemble project, there were 40 members that were produced using different initial conditions. They derived data on sea surface temperature, various atmospheric predictors. They applied machine learning models.
Коллеги, извините, с переводом проблемы. Сейчас мы слышим, что 2 переводчика параллельно переводят. Сейчас 2 переводчика параллельно переводят, извините. И предыдущий период у нас не было перевода. Вы можете вернуться, полистать обратно и заново вкратце рассказать, о чем было?
Sorry, Dinara, what's happening? Sorry, Sue, we cannot hear you anymore. We cannot hear you.
Hello, I'm sorry. Just now I don't listen for interpreter.
Okay, can you hear me now?
10 minutes, about 10
Yes.
minutes.
Okay,
Yes,
I'm just finishing up here.
Sorry, it was just because there's no interpretation for Russian. Sorry, there's that's.
Oh,
but yeah, 2 minutes. Yeah, 2 minutes, please.
Okay, and just wanted to point out that they had various different machine learning models, random forest, gradient boosted, neural networks, long short-term memory models. And when they compared that to the physical ensemble models, the red ones are the machine learning models, and we find that the accuracy of the machine learning models for both a November, December, January prediction, as well as a January, February, March one, the accuracy is at least as good, and in many cases better, for the machine learning models. So in summary, I've been trying to point out the variability of the atmosphere on multiple time and space scales. That really does impact how we operate energy systems, particularly renewable energy systems, as we go to higher penetration of renewables. We can predict these changes, though. For the weather, we use numerical weather predictions. We assimilate observations into our models. We use both the NWP and the observations to build machine learning methods to make that more accurate. And these predictions do provide real economic value to the energy system and the ratepayers, so that we can deploy more renewable energy because we know how to predict this variability. So thank you.
Fantastic. Thank you very much, Sue, for this nice presentation of all the elements that go into a short-term forecasting system. Sue has a huge amount of experience in doing so, as you can tell from the presentation, and hopefully we'll have some time for questions at the end. So please think about some questions, and also you can start typing them if you wish. So I would like now to move to the second speaker in this slot, who's David Brasher. And David Brasher is a professor of climate science and energy meteorology at the University of Reading. His research interests are large-scale atmospheric dynamics and its connection to human and environmental impacts. He has led a wide range of projects on weather and climate risk in the energy sector. For example, he recently participated in two important EU projects, Esem, the European Energy Climatic Mixes, and S4E, sub-seasonal to seasonal forecasting for energy, as well as an advanced climate modeling program called Primavera. So it's a great pleasure to have with us here David to talk about the next level of timescales up from short-term seasonal and from seasonal up to longer time frames. So it's a nice joint lecture between Sue and David. Over to you, Sue. Thank you. Excuse me, David.
Thank you. Can you hear me okay? Can you see the slides okay now? Sorry, there was a bit of confusion on the change.
Yeah.
They see them okay. Fantastic.
Yeah.
Right, well, thank you very much for having us here. And I guess to preface all this, I'll just say that I very much agree with everything that Sue has said. I guess what I'm going to talk about here is focusing a little bit on the fundamentals of climate, so the fundamental science behind it, rather than necessarily its application through into particular impact problems, but thinking about the fundamentals of climate and how it works. I'll also say that the content here is heavily bridged from an MSc course I teach on climate service and climate impact modeling, and if people are interested in that, then please do drop me an email to discuss. But what I'm going to try and do here is briefly go through the climate system and how it relates to weather, so sort of briefly review some of that and pick up on some of the themes that Sue's already mentioned. Brief talk on climate modeling tools, again, and picking up and expanding a little bit on what Sue's already said, and then have a little bit of a think about the types of prediction we're trying to make at climate timescales. When we're thinking, I would argue sort of climate timescales sort of weeks and beyond, everything from weeks out to decades and centuries ahead. We're also going to touch on the themes of uncertainty and error and how different modeling tools are used to address those. So that's roughly kind of the plan for the talk. So let's begin with the climate system. So at its heart, the climate system is quite simple, really, in a way. We have the atmosphere and the ocean and the various components. And the drivers of this are, as I say, quite simple. We have stronger heating exerted by the sun near the equator and cooling at the poles. So there's a heat gradient, if you like, a heating gradient between the equator and the pole. And that's on top of a rapidly rotating planet. We have the Earth spins very rapidly. I think it works at about 465 meters per second, the surface speed of the ground at the equator. And this is what gives rise to these large-scale features. Essentially, it's about heat and momentum transports through the system. A number of those features that are then produced are kind of well understood. We have a good grounding of why different large-scale phenomena exist. But in terms of our ability to simulate and predict these, it introduces a number of quite a number of challenges. So if you just direct attention to the plot on the right-hand side, the little animation going through, this is don't have to worry too much about what the colors exactly mean, but they represent a tracer of the motion in the atmosphere. So you can see the blue airs and the red air is swirling around. And they sort of essentially describe the weather features that we see on the day-to-day. So we have storms and blocks and the passage of mid-latitude weather systems. And we can think of climate in some sense as being the statistics of that weather. So climate isn't just about the average, it's about all possible statistics of the weather that may influence a particular region. So we have this sort of first idea of climate as being something about the statistical properties of weather. The second key component to focus on when we're talking about climate is that the climate system contains many different components that evolve on very different timescales. Yep.
David, sorry, I don't know if you got the message. If you could slow down a little bit.
Okay.
The interpreters are having a bit of trouble to keep up.
Okay, I'll do my best. Thank you for the warning. So just to recap then, the central point I want to give here is that the climate is about the statistics of weather. It's about the extremes, it's about the variations, it's about the averages, it's about anything to do with statistical properties of weather. So hopefully that message has gone across. The second area I want to just focus on with regards to climate is that the climate system contains many different parts and they evolve on very different timescales. So we're used to the weather being essentially the motions of the lowest 10 kilometers or so of the atmosphere. So this is what we call the troposphere, and it evolves on timescales of days. So the weather changes from day to day, and given a few weeks ahead, the weather may be completely different to the weather is today. So we have a relatively fast evolving, on the order of days, lower atmosphere. There are other components that we need to worry about for climate that evolve much more slower. The best and most obvious example is the deep oceans. Now, the temperature and the salinity of the deep oceans changed on timescale of centuries out to millennia. It evolves very slowly. And we have other components that sit in between these two timescales. So in particular, the upper atmosphere, the part of the atmosphere above about 10 kilometers known as the stratosphere, evolves on timescales of weeks or months. We have vegetation and land surface properties, such as the amount of moisture held by the surface, the amount of the heat of the temperature of the surface, which evolve again on timescales of weeks, months, and seasons. And we have other areas of the cryosphere, for example, that evolve on timescales of years. So different parts of the climate system evolve on very different timescales. It's not just the weather variations on day to day. There are other parts of the system that evolve on much slower timescales. This slow evolution part has important consequences for how we understand what we mean by climate. So the first challenge it introduces is the fact that the climate varies slowly. It can be very difficult to understand what we mean even by the present climate. So here's an example that I really like, that was produced by a colleague of mine, looking at the estimated lifetime income for a wind farm. So this wind farm, I think, was built somewhere in Germany. It's an imaginary wind farm. And this wind farm lasts for 20 years. And we assume the price of energy is constant over the entire time. So the amount of revenue we get from the wind farm depends only on the amount of wind that hits the turbine. And it calculates how much you would expect how much power you'd expect to produce from that wind turbine over a 20-year period. Now we think of 20-year periods as quite a long time. It's so the lifetime of a wind turbine. It gives you a lot of different weather over a 20-year period. But what you can see in the plot here is on the x-axis here, you have the year that the wind farm was built. On the y-axis, you have an estimate of how much what its lifetime cash inflow would be, depending on which, and it depends on which year you built it in. So take 100 as being the long-term average. But you can see if you built the wind farm in 1960, then you would have a much lower lifetime income than if you built the wind farm in 1980. So when you're deciding, whether that wind farm is viable, whether it's a good place to put it, whether it's a financially viable proposition, the estimate you get may vary quite substantially, just from depending on which decade you choose to build that wind farm in, which decade you use for your assessment of the viability. So the challenge that this slow variability introduces is this is nothing to do with climate change. This isn't anthropogenic global warming. This is just variations in the climate. The challenge that this slow variability introduces is you need very long baselines to be able to assess reliably what we mean by climate. So a year's worth of data or 10 years worth of data isn't sufficient. You need many years of data to reliably assess what we mean by climate. On the other hand, the fact that we have slowly evolving components of the climate system brings opportunities for prediction. Predictions weeks, months, seasons, even years ahead. And to give some examples of this, one example is the so-called stratospheric harbingers. So this is this top panel here. So the y-axis in this case is sort of taking a section through the depth of the atmosphere. So it's the dotted line here, the bit below the top, the dotted line shows the lowest 10 kilometers of the atmosphere. This is this fast evolving troposphere. And the bit above is the slow evolving troposphere. And the colors indicate a measure of the westerly flow. It's the strength of the polar vortex. In winter, we have a strong westerly polar vortex around the upper atmosphere. And what the red shows is when that vortex weakens, and when the blue when it's blue, it shows that it strengthens. What you can hopefully see is that when you have an onset of this weakening event, so we start to get these red colors, and so I should say the x-axis shows time and in days. When you start to get red colors in this upper part of the atmosphere, they persist there for many days. So they persist there for 30, 60, 90 days into the future. What you can hopefully also see is that those red features propagate downwards. They dribble downwards into the lower part of the atmosphere. So once we observe the onset of one of these events in the stratosphere, in the upper part of the atmosphere, we know it's going to persist for some time. And also we know that that's going to lead to the lower atmosphere, the bit that affects us and gives us our weather, to prefer a certain mode of behavior to another. So the fact that we know something about the upper atmosphere tells something about the lower atmosphere many tens of days into the future. And there are many such of these patterns, but they all hinge on these slow evolving parts of the climate system. So particularly another example is things to do with sea surface temperatures. So here we have a mode of variability called the Pacific Decadal Oscillation, and you can hopefully see that the differences in surface temperature patterns over the ocean, they have an imprint of consequences of what that means to the weather across the globe. So we can use this slowly evolving part of the climate system, this decadal scale variation in ocean temperature in the Pacific, to tell us something about the weather behaviors in and around the globe. So you're using these slow part system to give you predictability for the weather across the globe. Is my speed okay now? Are the interpreters managing to keep up with me now? I'll assume yes, unless you tell me otherwise.
Yeah, I guess so.
Fantastic. So for the second part of the talk, I want to briefly talk about and introduce climate modeling, climate data. So if we're talking about producing climate services, we need data from somewhere to produce those services. So where does that data come from? So the most obvious data set that most people think of immediately is observational data. So you have weather stations or you have satellite data to provide some sort of estimate of weather at some locations. Now, both these resources can provide very high quality estimates of meteorological properties at wherever they're sited. I mean, they're fantastic. They are the gold standard, if you like, for observing the weather at particular locations. But in terms of providing climate services, they can have their problems. In particular, the observation networks tend to be quite sparse. And I've tried to give an illustration of that, the kind of problem that introduces. So let's suppose we have a wind mass measuring the wind speeds at the two blue dots. And the colors on the map on the background suggest topography. So this is the brown area is a mountain and the green areas are valleys. If I have two weather masses in these two valleys, but I want to build a wind farm on top of the hill, it's not necessarily obvious that the data from those two met masts will necessarily be very useful for predicting the wind speeds at the top of that mountain that lies between them. Even just interpolating on a line in between them isn't necessarily going to give me a good estimate of the wind speeds over that mountain. So you say, well, okay, so we'll build a new met mast. Well, that's fine. But then you've built that met mast on top of the mountain, but then it only exists since you built it. You can't use it to generate a long historic record to really reliably characterize what the climate is over the mountain. Even if there had happened to be a met mast on that mountain, then it's that often the instruments break and they change and they evolve over time. So there can be quite disjoint records of weather phenomena over time because someone's changed the observation instrument from one type to another type. Okay, so maybe let's look at satellites. So let's think about a satellite. Well, what the satellite is observing is a radiation pattern. It's not directly observing the wind speeds or the temperature. So there has to be a model that links the observation the satellite takes to the weather property we're interested in. We call this retrieval. So there are issues with those models. You know, those models themselves may not be perfect. We can't use all the satellite data that we're presented with anyway. There are problems in cloudy regions or regions over complex terrain or over sea ice that can cause problems. So the point I want to make is that observations are a fantastic resource, but they're not without their problems. There are limitations to how far you can go with climate observations. So that brings us to the subject of models. We might want to use models to support our understanding and our data sets we might wish to use. And Sue has already mentioned numerical weather prediction models. So my take on this is, you can imagine we have the atmosphere, we divide it up into grid boxes, we write down the equations of motion for those grid boxes. So they're based on a version of Newton's laws called Navier-Stokes, but essentially they're well-established physical laws. Those grid boxes have a certain size. They're typically several kilometers across, several kilometers by several kilometers. So there are things that happen within the grid box itself. So we write down extra physical models for the processes that occur within those grid boxes, such as clouds and moisture exchange, surface energy and radiation budgets. And we put this model together and we feed in our guess of the initial state as it is today. We run that model forward a time step at a time. These models work iteratively. They do time step at a time. And we run that model forward so that it produces a prediction of what the future weather state would look like. And this is essentially the bedrock of every numerical weather prediction scheme. It looks a bit like this. It's essentially dividing the atmosphere into grid boxes and running initial states forwards in time to produce predictions of future states. An important subdivision of this is actually called Reanalysis. So we can use these weather models and combine them with historic observations. Sue's already mentioned this process of data assimilation. So it's sort of a merger of these two sources, and they can produce very long duration, high quality resources of gridded 3D weather. And essentially the process looks like this. We have an estimate of what the atmosphere looks like today. We run that forward in a numerical weather prediction model by, let's say, 6 hours. After 6 hours, we have a fresh set of observations coming in. We merge our model prediction, which is a very good prediction, with our observations, which are very good assessments of the climate system now. We merge those together through data assimilation, and we repeat the process. And we we run the model 6 hours at a time, and every time we add a fresh set of observations, we merge those two together. The net effect is that we produce a 3D gridded reconstruction of the entire atmospheric circulation. Those are fantastic resources, and for me, they're my go-to starting point for most things I do to do with climate and climate, whether that's climate research or climate services. They still have their issues. They typically have grid boxes of 50 kilometers by 50 kilometers or 30 kilometers by 30 kilometers. There are issues with changing observation data sets. So pre the 1980s, there were relatively few satellites observing the weather, so there are change in quality because of that. Models aren't perfect. They have deficiencies. Some variables in particular are simulated better than others. And they're obviously backwards looking. We're assimilating historical observations with a numerical weather forecast model. So it's backwards looking, it's historic. It has no direct representation of future climate. So if we start to concern ourselves with future climate, we then need to turn to climate models. So we start to think about Gcms. These are very similar to numerical weather forecast models, as Sue's mentioned, but they tend to be low resolution, but they include more processes. So as well as just the atmosphere, we now need to worry about those slower evolving parts of the climate system. So climate models tend to have more representation of more climate processes, particularly the oceans and the cryosphere, but they tend to run with larger grid boxes for much longer time periods than do the numerical weather forecasts. So there's this kind of trade-off. And I think this is kind of where I want to just leave this bit of discussion. It's a big subject, so it's beyond the scope of this lecture to get into. But essentially, choices are always made. There's always a trade-off between how big the grid boxes are versus how long you can run the model versus how many processes you can represent. So there's always a kind of trade-offs in choices in the modeling framework. All models are wrong. It's just some are useful. They have biases and deficiencies. You can assess these and correct them and understand their limitations, but that's an essential step in anything. A point to be aware of is that climate models often brag about how small the grid boxes are, how fine scale the detail is, which is great, and the grid resolution is important. But just because you have data that exists at 10-kilometer scales doesn't mean that necessarily the scale that the model can actually represent physical processes at. And it's important to be aware of the quality of the output variables that you get. And we'll come to this a little bit more later. The point I really want to leave you with in all this discussion about the data is that there is no perfect data. There's a lot of very useful data sets and very useful data sources for climate services, whether they're observations, whether the model runs, or some kind of merger of the two. But there's no perfect set of data that's useful for all applications. So whatever application you use the data for, it's absolutely essential that you validate its ability and its qualities for that purpose. It's not that there is no perfect assessment. You have to do it for the thing that you're using it for. You can't just rely on general assessments. So I think that's all I want to say about models. Let's think about the predictability we're talking about. When we're talking about climate predictability, what do we actually mean when we're trying to predict and forecast climate? So to illustrate this, I want to use a very simple example. So here we have a pin board. Balls are being dropped onto the hopper at the top. They're bouncing down the pins and dropping into the buckets at the bottom. You can think of each ball as a weather sample. It's the weather that happens on a particular day. You can think of the pins as being the chaotic behavior of the atmospheric system. The atmosphere evolves over time and it bounces along and it produces a fresh state at some time. And the buckets at the bottom are the weather property on a particular day. So here I've sort of, in this cartoon, I've said that the balls that fall to the left are drier days and the balls that fall to the right are wetter days. And you think of this hopper at the top moving left to right, which corresponds to the day's weather that you're starting your forecast with. And bouncing down the balls is the length of the forecast. Bouncing down the pins gives you the length of the forecast. The first type of predictability we might think about is a climatological prediction. So we said that it's quite hard to know what the climate actually is. What do we mean by present climate? Well, I would take it as being the distribution of the balls at the bottom. Once we've thrown enough balls down, we know they tend to prefer to fall in the middle buckets rather than the edge buckets. So we know something about the distribution. That's our understanding the range of possible weather that we get in present climate, if you like. That's a good characterization of historic weather. But when we think about prediction, we usually think about something slightly different to that. We think about predictions of meaning the future, where we know something about the future. The first type of prediction is what's called initial condition predictability, sometimes referred to as type 1 predictions. So let's focus on one particular ball, this red one. The question is, which bucket will that ball fall into? And the analogy to this is predicting the weather 3 days ahead. We know the weather today, we know where the ball's starting, but we don't know where the ball's going to end in 3 days' time when it gets to the bottom of the pins. And things that will help us to predict that are knowing exactly where in this space this ball is being dropped. So is the hopper, has it moved to the left? Has it moved to the right? Will have a very strong influence on which bucket the ball drops into when it gets to the bottom. So knowing something about our initial state, where we start from, gives us a lot of information about where we're going to. Now, the issue with weather is that for the lower atmosphere itself, that kind of thing, that kind of knowledge gets lost. It's washed out after just a few days. So that gives us the limit of our weather forecast range, is the state of it from the atmosphere. But it's something about our starting positions that matter. The second type of predictability is what we might call boundary condition predictability. Here you can think about the balls dropping at the top again, but now we've tipped the frame to one side. So the balls are going to prefer to fall left rather than right in this example. An example of this is thinking about a climate change prediction. So at the end of the 21st century, we know we're going to have more greenhouse gases in the atmosphere than we have today. It's very likely, depending on mitigation strategies, how much we manage to avoid climate change. But in general, we know there's going to be more greenhouse gases. And most of the models are run assuming more greenhouse gases for 2100. The question is, that's sort of tipping the climate system in a way. And so that the balls of the weather is going to prefer to fall one way rather than another. But the source of predictability is now coming from how hard we've kicked the system. And that's where our prediction skill is coming from. It's a boundary condition problem. It's how much we've tipped the boundaries of the problem. So when we think about climate prediction, we're dealing with a bit of a mixture of this. In terms of weather and climate prediction, we tend to think of a range of different scales. Oops. And the range that Sue focused on, not exclusively, but focused on, was kind of down this left-hand end, where we're dealing with predicting things hours, days, and weeks ahead. There, we're relying on initial condition prediction of the atmosphere. So if we know the atmosphere now, we can say something about it a few days ahead. If we go to the opposite end and we're dealing with predictions of how climate's going to change over several decades ahead, then we're dealing with kind of projections. We're saying, if greenhouse gases increase by this much, then this is what the weather and climate state will look like. So we're making boundary condition predictions. One of the most interesting spaces in my world for research purposes is this bit in the middle, this extended range weather forecasting, seasonal forecasting, decadal forecasting. Because there, as far as the atmosphere, it's a boundary condition problem. But as far as the slower components of the climate system are concerned, it's an initial condition problem. If we know something about the ocean today, we can say pretty confidently what it's going to look like in a month's time. So we're relying on the slow evolution there to give us this predictability that feeds into the atmosphere. And that's kind of where this mixed space lies. And so when we're talking about these kind of predictions on weeks to months to years ahead, it's this kind of mixed space problem that we're dealing with. So finally, I'm coming towards the end now. So I just want to briefly talk about climate uncertainty. And yeah, as a hazard warning again, I'm trying to focus on kind of what I would see as some of the most important essentials. All models have limitations, and Sue gave a great series of examples of how we go through this chain from the weather and climate through to the user decision at the end. And it's vital to assess and understand the errors and uncertainties at each step of that chain. Here I'm going to focus on the meteorological part of this, and particularly focus on the use of ensembles. Sue again mentioned ensembles, and these are at the heart of the climate forecasting process. Now, there are two kinds of ensembles in the main. The first type is the initial condition ensembles. Remember, we talked about this idea of, we didn't know exactly where the bucket was at the top, and we're trying to predict the path of a particular ball down the pin board, or days ahead weather forecasting. The issue is that we do not know the state of the atmosphere, the state of the climate system perfectly now. There are a range of different possible starting states. So the errors in our knowledge of our initial starting state grow rapidly over time. That's the core problem. So instead of starting with just one estimate of where we are today and running that forward to produce a prediction, we take many different possible starting states, consistent with our knowledge of what the climate system is looking like today, but they're slightly different from each other. All of those then run forward, and they give you a spread that's much greater into the future. So you can see how those pathways sort of spread out over time. So we end up with an ensemble prediction. We have multiple possible outcomes that might happen. And what we're trying to do is sample the errors that are coming from, or the uncertainty that is coming from, our lack of knowledge about the climate state today. That's the first type. The second type are so-called multi-modal ensembles. Now, we talked about climate models, we talked about how they're built. Different climate models have different ways. Sorry, apologies, my son just came. Tom, can you go down and see your mum now, please? Go and see your mum. Go. Sorry, I'm just showing my son out there. Just come show him some apologies. So different models have different ways of representing the climate system. They have different ways of writing down the same equations, if you like. And as a consequence, they respond slightly differently to forcings when they're applied. So they respond slightly differently to the way greenhouse gases affect them. So rather than running just one model, we might look at many models. And the extent to which they give a consistent response across the models may give us confidence in that prediction. So an issue with this is the interpret.
Sorry, David, are we wrapping up?
Yeah, so wrapping up now. So yeah, sorry, I'm trying to talk slowly. I still go fast. The interpretation of these things can be quite challenging. The simulations are capturing different things, including this slow variation, which is a form of initial conditional uncertainty. But a key point I want to get across is that people spend a lot of time looking at this multi-model average and this multi-model combination, but the models aren't necessarily independent estimators of that future truth. So I would encourage people to look at the storylines-based approach for understanding how we interpret future climate scenarios. There's a lot of work on it, and I'll refer to this reference by Shepard to look at it in more detail. So here we go, here's my conclusion. So we've briefly reviewed basically what the climate system is. We've talked about the modeling tools, and we talked about the different types of climate prediction and how that relates to uncertainty. This is a massive subject, and if you're interested in going further, I'd love to hear from you. We have an online course that covers much of this in a bit more depth, and we have these webinars coming up. If you want to talk about any of this in any more detail later, then I'll love to chat. I'll wrap up there. Thank you.
Excellent. Thank you very much, David and Sue. So yeah, this was a lot of information packed, but provided in a very digestible way, apart from the speed at the beginning, but we adjusted it and it was working. So we are over a little bit over the time, as it usually happens, but we want to take a few questions. So please, if you could stay on for a few more minutes. The participants, I know it's getting late in Central Asia, 6:30 p.m. So we'll take a few questions. We have here in the chat 2 questions to start with. So I don't know whether they are, who they are for. Let's say whoever wants to responds. So the first one is, how is vegetation and changing vegetation cover deforestation being integrated into the weather and climate models? There used to be a mid-speed change and now they're fast changing.
I'll have to try and speak to that. I don't know too much about the details exactly of the scenarios that are used in the Cmip round. So people may have come across the Cmip project, which is a coupled modeling comparison project. Essentially, it's the simulations that go into the IPCC reports, effectively. They have a well-defined set of scenarios that are thought about very carefully in terms of emissions, land use change, and so forth. I'm not exactly sure the protocols that are in there, but in principle, the models certainly can cope with that vegetation change and land use change. I don't know exactly how they're integrating those in these particular simulations.
And I would say on the weather timescales, we certainly have land use, land cover information in the models, and it gets updated seasonally, as well as when there are these longer term changes as well.
Okay, thank you. And there is another related question, which is, will the land use, land change affect the wind patterns on a small or large scale?
It certainly will on the smaller scales to some extent. One of the more important variables in getting temperature right, which is important for getting wind right, is soil moisture content, which of course is controlled by land use, land change. So at least on the smaller scales, we are likely to see changes, especially as that changes the temperature, soil moisture, etc. Large scale, as David pointed out, we have the large scale circulation that is dependent on the radiation coming in being stronger at the pole, at the equator than at the poles. David, would you like to elaborate?
Sorry, which sorry,
okay,
which bit?
Yeah,
elaborate on which bit?
Yeah, on the large scales, I don't see the winds changing so much as on the small scales. Would you agree?
So yes, I'm not totally familiar on this in a worldwide context. There's been a lot of discussion around wind speed changes over Europe, and there's been a lot of discussion around whether they're possible stilling trends or not. I would say that the jury's a bit out on that. Certainly for Western Europe, the changes seem to be relatively small compared to the variability that exists already, but I would say the trends are quite uncertain. But as a large scale thing of will the westerly winds disappear? No, I don't think there's any evidence of that. I think that there will be influences, but it's probably relatively small in that sense.
And I was actually chatting with some people in the Arctic yesterday, and they're seeing changes in land cover over relatively short timescales, periods of a decade. And they are concerned that they're, basically the canary that where we're seeing it first. And that is making a bit of a difference in their wind patterns, and they really are trying to consider that as they're planning where to put their wind farms in the future.
I certainly think that there's a lot of investigation to be done in that space. I don't think we really know is the answer. I think the changes may be quite subtle. I think that might be the issue.
Mm-hmm.
Yeah, I mean, to just to integrate a bit what's been said, particularly you David referred to changes in Europe. Actually, the changes have been observed worldwide, And they are attributed at this stage to the change in circulation, so north-south circulation, which is driven by the heating, again, the differential heating you talked about, but this is because of the global warming. And so the circulation is expanding, and with that, also the wind patterns will change. And it actually could be the opposite effect, that the wind changes could affect the land change because of the way in which the wind affects the vegetation. So there is an interplay there, and there's a lot more to be done, but it's an interesting area. We'll take one last question here. From Priyada Srini, and sorry for the mispronunciation, I just wanted to attribute it. So do we consider surface wind velocity or vertical wind velocity for the establishment of wind farms?
Okay, so what really is used is what we call the horizontal wind at hub height. So hub height is where that nacelle of the wind turbine is. It's anywhere from 80 to about 120 meters above the land surface, depending on the size of your turbine. And when they do resource assessments, they use long-term average statistics, like David was talking about, estimating the hub height horizontal wind. So the wind that is parallel to the surface. The vertical wind certainly occurs, but it is typically at least an order of magnitude smaller and not what we're harvesting with the conventional type of wind turbines that we use today.
Thank you very much. I don't know if you want to add anything to that, David?
No, I agree with that entirely. I think I guess one thing that has been discussed a bit has been shear. So not so much the vertical motion of the wind, but the differences in the horizontal wind with height. And I think there are a number of questions around that, and there has been mentioned about jets impacting the top part of the turbine circuit, if you like, and can having quite a damaging effect on turbines. So I think there are, as a gross measure, I think people look at horizontal wind at turbine height, but there is also issues of turbulence and vertical shear that people might want to think about.
Yeah, indeed. I mean, these are becoming huge structures, and they can get up to 150 or more meters. No, so with the tip of the, or even higher. So that's some new challenges for meteorologists, and to talk with energy producers of wind power in this case. So I would like to wrap up, and in doing that, I would like to thank you very much, David and Sue, and particularly Sue for waking up so early for us, but obviously also David for handling well the child coming in. And of course also Claire in the previous session, and all the participants. Hope you had a good session there with the working groups, and you keep up the good work towards the final presentation next week. We have 2 other working group sessions, Monday and Wednesday, and we are then reconvening the training on Monday, 10 a.m. UTC as usual. So we look forward to seeing you. Have a great weekend. See you soon. Bye.